time invariance, we are going to call it as a linear system. So the x of t will be the input, output will be the y of t, and the corresponding impulse response or the system function can be defined in terms of the h of t we are going to define. Okay, so this h of t is nothing but impulse response. You see all the definition in the convolution in your signals and systems. And the output is nothing but it's a convolution integral we can give here, convolution integral. And also, you know, the convolution is going to satisfy the property of commutative property. We can write like this here. Okay, so this is a convolution. So you can take where h of t is the, so this is a convolution integral. So here we are not define what is h of t, where h of t is the, where h of t is the impulse response of the system, impulse response of the system, impulse response of the system. So right, in the last class we had taken up to this this point we had taken here. Now h of t is nothing but the impulse response of the system. Now usually if you look into the how you're going to model the system, so I think in your control systems you have seen, so the control systems already you are going to see the unlock systems. You are going to see unlock systems is nothing but, so it is having some feedback systems will be there, the unlock components which you are going to make use of the in the last semester we are seeing the network theory. Okay, so which contains the resistors, capacitor, inductors, those are nothing but the unlock components. Okay, so for the unlock components, in order to model the unlock system, so the components which are the system which is made up of the unlock components, we are going to call it as the unlock systems. Okay, so in order to model the unlock systems, you are going to make use of the Laplace transform. Okay, so why? Because sometimes in the time domain we cannot able to obtain the solution. So the solution we are getting in the infinite solution we are getting here. So at that time, in order to overcome that one, in order to get the finite solution, we'll take the Laplace transform so that the signal will be converted into the from time domain to the S domain. S domain, you are going to call Laplace transform as the S domain. So there we are finding the solution and we'll take the inverse Laplace transform. So in order to get back the solution in the time domain. Okay, so similarly for the discrete time systems, which you are going to define in terms of the y of n is equal to x of n convolution with h of n. So in order to model that one, we'll go for the Z transforms. Okay, so Z transforms you are going to use that you are going to study in your signals and systems. Okay, so now since it's an unlock system, I'm going to take the Laplace transform for this one. Okay, so for this system, I'm going to find out the mean, autocorrelation, cross correlation, and let us find out the remaining parameters. Okay, so you can take in the frequency domain. In the frequency domain, the system can be represented by in frequency domain, the system can be represented, the system can be obtained by taking Laplace transform, obtained by taking Laplace transform, Okay, we can call this as equation number 1. You can call here Laplace transform of equation 1. Laplace transform of equation 1. So if you take the Laplace transform on both the sides here, so what is the Laplace transform of y of t is nothing but y of s, and the x of t is nothing but it's a x of s. And also, you know, one of the property of the convolution in the time domain will become equal to the multiplication in the frequency domain. Either it may be Laplace transform or Fourier transform or Z transform. So any transforms you're going to call it as a frequency domain you're going to call. Okay. So you can take x of s and h of s, x of s and y of s, or Laplace transform of x of t and y of t. X of t and y of t. H of s is the transfer function. We are going to call this one as the transfer function you are going to call. So in the Z transforms you will come, we are going to study in detail what is the meaning of the transfer function and everything here. So is a transfer function. So the transfer function is the thing which you are going to obtain in the input output relation you are going to obtain. So that one you are going to call it as a transfer function you are going to call. For example, if you are going to solve h of s, so h of s will become equal to the y of s divided by x of s you are going to get here. So that one we are going to, the system which is represented in the S domain or the Z domain or the frequency domain, you are going to call it as a transfer function, which is going to transform the input to the output it is going to transform. That's why it is called as a transfer function you are going to call. So transfer function of the system It is called as the transfer function of the system. So right. Now what we are going to do is for this system, which is represented in terms of the y of s, h of s, we are going to find out the mean, cross coefficient, and many parameters. Let us see those parameters now. So take and write. Okay, so we'll find out the parameters. So take first one, mean. The mean of the linear system is given by the mean of the linear system is given by So this can be given by the formula like this. So the mean of the y of t or y of s will be equal to nu y will be there, and the mean of x will be x here, and at s is equal to 0, or the frequency at s is equal to, we know that s is equal to sigma plus j omega. So by substituting omega is equal to 0, so that we are going to obtain at s is equal to 0, we are going to obtain. So this is the mean we are going to consider, where the frequency will be set as 0. At omega is equal to 0 or s is equal to 0, we are going to obtain the. Okay, so this is the corresponding value we're going to get in for the transfer function. So right. So similarly, we'll find out the cross correlation. So again, take cross correlation. So we are going to take the formula. So we are not going to do any iteration. Cross correlation of x of t and y of t. Cross correlation of x of t and y of t is given by. So we know the cross correlation formula. So cross correlation is nothing but, so it's a rxy of tau. So this will be equal to the, so it's a rxy of tau. It is nothing but it's a cross correlation of the x of t and y of t here. So that is expected value of the x of t and y of t are going to take. So x of t and y of t plus tau will be taken here. So this is nothing but, we can represent this one as a, so x of t, the cross coefficient of the x of t is nothing but it's a x of tau, or x of tau we can take here, and since the y of t is nothing but it's a convolution of the two things will be there, so we can directly write that one as a h of t we can write here. So rx of tau convolution with h of t we can write. Rx of t convolution with h of t. So this is a cross correlation of the x of t and y of t. So when you're going to solve this one, you're going to get, so we are not going to solve, just we'll take the formula. Okay. Similarly, we are going to find out the cross spectral density. We are going to find out the spectral density is nothing but, if you take the Fourier transform of this one, you are going to get the power spectral density. We are going to get right by taking the Fourier transform of the autocorrelation function. So similarly, for the cross correlation, if you are going to take the Fourier transform, you are going to call that one as the cross spectral density. You are going to call cross spectral density. So take cross spectral density. So this is obtained by taking the Fourier transform of this one. We can take cross spectral density. Cross spectral density is obtained by taking Fourier transform of rxy of tau. So if you take the Fourier transform of this one, so it will become the Fourier transform of the, we are going to denote as a sx of f, you are going to denote, or sx of omega. So this is sxy of j omega e to the power of j omega, all are one and the same here. You are going to study in the Fourier transform, because this is a representation in the Fourier transform. You are going to represent like this: j omega or omega or e to the power of j omega, all gives the same meaning. So in the frequency domain, we are going to call here. So all having the same notation. So the Fourier transform of h of t is nothing but h of j omega, and you know that the convolution in the time domain will become equal to the multiplication in the frequency domain. So this can be written as sx of j omega. Sx of the Fourier transform of this one is sx of j omega. So this is the power spectral density. This is a cross power spectral density. This is the Fourier transform of the impulse response of the system. impulse response of the system. Okay, so this one you're going to call it as a cross spectral density. You're going to call cross spectral density. Similarly, let us find out the power spectral density. Let us find out here the power spectral density. Okay, so you can take power spectral density, power spectral density of y of t, power spectral density of y of t. Okay, the power spectral density of y of t. So this is given by the formula. So it will be equal to the sy of omega. So the power spectral density as sx of f as sx of omega. So it will be equal to the magnitude of h of j omega, the whole square, into sx of omega, into sx of omega. Okay, so this is the power spectral density in which you are going to obtain. So since we know that the y of t is ultimate, it's a convolution of x of t with the h of t. So when you take the Fourier transform, when you are going to consider the magnitude, so power spectral density is ultimate, it is going to give the magnitude of the signal. So we already see in the previous class. Okay, so the power spectral density is it's a magnitude of the signal. So that can be expressed in terms of the, so like this we can express here e to the power of x of j omega magnitude the whole square. So the similar way it has been considered here. The similar way it has been considered, so that the power spectral density of y of t, which is nothing but sy of omega h of j omega magnitude the whole square into sx of omega. So this is the power spectral density of y of t. So right. So any doubts? So what we have seen so far is we have considered the linear system. So the linear system is the ultimate. It is the LTI system. For that one, we taken the output is the convolution integral, and for that one, we have taken the Laplace transform, so that we got the system in the S domain. We got here. For this system, we find the mean, we find the cross correlation, we find the cross spectral density and the power spectral density. So that's about the linear system, where how we can modify the. So the convolution integral can also be applicable to the system which is random in nature. So usually all the systems which you are going to consider in the design of the receivers, those systems are nothing but the linear systems, and the input for that one will be the random signal you are going to get. The random signal is the limit. So you're going to transmit the data in terms of ones and zeros. For that one, the noise will be added. So that noise you are going to call it is the white noise you are going to call. So let us see how the white noise will be there. Okay. Let us see how the white noise will be defined. What is the power spectral density of that one? That is the mean of that one. So let us see all those things here. Because in the communication, so usually we are going to model the system. In order to find the system, we are going to consider as a white noise system. We are going to consider white noise. So by considering the white noise, we are going to define the some power spectral density of the white noise we are defined. So based on that one, we are going to find out the how the probability of error is going to vary for the system. So let us see that one. So that is nothing but the last concept in this model, which is called as a noise. So noise is nothing but it's an unwanted signal. So because the noise will be generated because of the many parameters, because of the variation in the atmospheric condition, or because of the at the receiver end, front end of the receiver end. So if the receiver is working continuously, you know about your mobile phone. Okay, if it is working continuously, what will happen? Your mobile phone will get heat up, right? It will get heat up. So at that time, what happens? Because of the heat generation, the some noise will be generated. That noise you are going to call it as a thermal noise. We are going to call thermal noise. Because of the heat, the noise will be generated. So because of the atmospheric conditions, so because of the if the humidity is more, okay, if it is a rainy nature and if the cloudy nature will be there, then the signal will be get faded, or it is getting slowed. It has been getting delayed here. So there's some kind of noise will be added here. So in general, we are going to consider the noise as a white noise. We are going to consider. Okay, so you can take consider a white noise. Consider we are going to consider white noise. That noise you are going to call it as a n of t. You are going to call. Okay, so for this white noise, the mean of this white noise will be equal to 0 will be there. So mean is ultimate. So the signal will be keep on varying like this. So the signal will be keep on varying like this. If you're going to calculate the mean of this one, this mean will be equal to 0 will be there. Okay, and the power spectral density of this one is going to vary. That value will be equal to some constant which you're going to call it as n0 by 2. Okay, let us see that one. So you can take consider the white noise random process. Consider a white noise random process. Consider a white noise random process n of t. Consider white noise random process n of t, which has so it is having a 0 mean. zero mean, which has zero mean, which has zero mean, and constant power spectral density, and constant power spectral density. In short, I'm going to call it as the PSD at all frequencies. At all frequencies. At all frequencies. So usually the power spectral density of this white noise will be equal to constant will be there. So this is for the frequencies range up to the 10 to the 12, 10 to the power of 12 hertz, it will be constant will be there here. Okay, so 10 to the power of 6 is mega, 10 to the power of 9 is giga, and 10 to the power of 12 is nothing but terahertz. Up to the 1 terahertz, the signal, this frequency, the power spectral density of the white noise will be constant will be there here. Okay, so it will be constant, and that constant value will be equal to some n0 by 2. So when you are going to model the communication system for designing the receiver, at that time they are going to assume some parameter. Based on that one, the power spectral density of the white noise will be defined. Okay, so you can take practically white noise. Practically white noise as a constant. Practically white noise has a constant PSD. Has a constant PSD for all frequencies. For all frequencies less than 10 hertz, less than 10 to the power of 12 hertz, less than 10 to the power of 12 hertz. Okay, less than 10 to the power of 12 hertz. So up to 10 to the power of 12 hertz, it will be having the constant value will be there. So that constant value you are going to denote as the K we are going to denote here. Let us see that one. We can take the power spectral density. The power spectral density of idealized, the power spectral density of idealized white noise, idealized white noise, okay, idealized white noise, random process. So this is called as a random process, n of t. So this white noise you are going to denote as n of t is given by, so the power spectral density is ultimate. You are going to denote as S is the term you are going to use denote the power spectral density. So it is Sn of omega. So this Sn of omega will be equal to K. Okay, so from minus 2 pi into B is less than equal to omega is less than equal to the plus 2 pi into B, and it will be 0 otherwise. So this is the value which you are going to define here. This is the value. So that is, it is having the value, constant value from minus 2 pi B. So since it is the omega is nothing but it's the angular frequency, you know omega is equal to, it is the 2 pi of, we are going to call it as the angular frequency you are going to call. So this is going to vary from minus 2 pi B to the plus 2 pi B, plus 2 pi B. So this is the angular frequency. This is the Sn of W. Okay, so this value will be equal to K. This value will be equal to, say, it is uniformly distributed between these two frequency ranges. So here we are going to take this one. Okay, taken, right? Now here the term B is called as a, it's a bandwidth here. So you can take where B is the bandwidth. B is the bandwidth. So bandwidth of the signal which you're going to transmit here. So omega is nothing but the, it's an angular frequency. Angular frequency. Okay. So take the next line. The variance of the, so let us find out the variance here. So these variants are defined, the constant values it has been defined here. Just we are going to see what are the values of these variances. Okay, so in the next semester, in the 5th semester, in the subject called the principles of communication systems, you are going to study the different kinds of noises you are going to study. Okay, so at that one you are going to study white noise, thermal noise, Okay, many kind of noises you are going to study. Okay, so at that time we're going to see all these details here. So you can check the variance of the white noise is given by variance of white noise is given by variance of white noise is given by. So this is denoted as a sigma n square, which will be equal to the 2 into k into b, 2 into k into b, k into b. So here k is nothing but already we have seen that is nothing but that it's the power spectral density. So that we can find out from this one, we can obtain the value of k. So k is the power spectral density. K will be equal to the, it is a sigma n square divided by 2b. Sigma n square, sigma square n divided by 2b. Where sigma square n is nothing but it's the variance of the signal, and 2b is nothing but it's a bandwidth. Okay, so we can define the k is nothing but this one. So here also the k can be given the same value. It can be denoted as, it is a sigma n square divided by 2b we can denote. Okay, so this is the variance of the white noise. Okay, so take the next line. The noise power, the total noise power we can take. So total noise power is given by, total noise power is given by, so the power of this noise will be denoted at for the autocorrelation function at omega is equal to 0 we are going to define. So this will be equal to the 2 into k into b, 2 kb. So this is the total noise power. So usually this will be considered same as the variance you are going to consider. This will be same as the variance it will be taken. Okay, so we can take, so from this one we come to know that it is having the this is the power spectral density of the variance, because we have substituted k. So this k will be equal to the, this k will be equal to the Sn of omega, this k will be equal to Sn of omega, so that it is having the constant power spectral density will be there from the minus 2 pi omega to the plus 2 pi omega. Already I told this one. So it is uniformly distributed within these range of frequencies. Okay, so this is a kind of the white noise which will be having the this one the variance. Okay, and this is having the noise power, thermal noise power at omega is equal to 0. It will be, this is the thing we are going to consider. So similarly for the other kind of noise we are going to consider, which is called as a thermal noise. So this thermal noise is nothing but the noise generated across the resistor. So because when you're going to pass any current through the resistor, so there will be some kind of noise will be generated, because you know resistor is nothing but it is going to oppose the flow of current. For example, you might have observed in your previous semester AEC lab. Okay, so when you're going to pass that one, after some time the resistors will be get heat up here. And also for the each and every resistor there will be some wattage will be there, power wattage, that is the power wattage dissipation will be there. So usually the wattage dissipation will be, suppose if it is a 1 watt resistor, you can see the size of that one, bigger one will be there. If it is a 0.5 watt, the size will be smaller one will be there. So that when it is passing here, the heat will be generated because of opposing the current here. So because of that one, the noise will be the heat will be generated. Because of that one, noise will be generated. That noise we are going to call it as a thermal noise. We are going to call here thermal noise. Okay, so you can take thermal noise. Let us take here thermal noise. So this is the noise generated because of heat generated across any of the components. Usually it will be taken as a resistor here. Thermal noise. The noise generated across the noise generated across the resistor is called as thermal noise. Is called as thermal noise. Okay, thermal noise. So usually this thermal noise will be denoted like this here. So it is given by the factor that is the RMS value of the voltage which you are going to given and the corresponding resistance. So already I think you might have seen in the design of the in the last semester in the electronic devices you have seen this one. So here where K is nothing but it's a Boltzmann constant. So K is nothing but it's a Boltzmann constant. Boltzmann's constant you are going to call. Boltzmann's constant. Okay, so T is nothing but the absolute temperature. So it is called as the absolute temperature. across the resistor, auxiliary temperature, and B is nothing but it's a bandwidth. B is nothing but the bandwidth. Okay, B is nothing but the bandwidth. So now for this thermal noise, there will be a power spectral density which we can define in terms of the Boltzmann constant and the temperature across the resistance and also the value of the resistance. Okay, taken right. Okay, so let us take the power spectral density. The power spectral density of the white noise. The power spectral density. Sorry, not white noise, thermal noise. You can take the power spectral density of thermal noise. The power spectral density of thermal noise across resistor R. Across resistor R is given by. So this is nothing but SR of omega. So for the resistor we can denote like this. So it will be defined as 2 into K into 2 KTR. 2 KTR. Okay, so done. So this is the power spectral density. Next, let us find out the total noise power we can find out in terms of the autocorrelation function. So you can take total noise power. Total noise power is given by, so it is nothing but Rx of 0. So it will be equal to the 1 over 2 pi. So integral from minus 2 pi b to the plus 2 pi b SR of omega into d omega. SR of omega into d omega. So this will be equal to the, so almost we are going to get this value is equal to the 4 kT into BR. 4 kT into BR. Okay, so this is Rx of 0. So we are going to get this value, and already we defined this is equal to, so Vrms square is nothing but Vrms square by R is nothing but 4 kTb. So since R is cross multiplied, so this one you can get to the Vrms square. So you know the root mean square value. So you are seeing it's a root of the mean of the square of the signal. We are going to call it as a root mean square value. So right. So this is the total noise power across the resistor, which is generated because of the thermal noise. So usually this noise across the resistor, we are going to consider as a white noise. We are going to consider up to the frequencies which is less than the 10 to the power of 12 hertz. Okay, so it will be considered same as the white noise. So whatever the power spectral density is going to generate, it will be same as the white noise will be there. Okay, so you can take the noise across resistor. Noise across resistor. Noise across resistor R is considered as white noise. Is considered as white noise. Is considered as white noise and valid up to so B is less than or equal to the 10 to the power of 12 hertz. So for the frequency or the bandwidth of the signal, it is up to the 10 to the power of 12 hertz. It is having the constant value will be there. Okay. So this is about the white noise and the thermal noise. These are two types of noise we are going to consider, which is random in nature. In the communication, we are going to consider this one, and we are going to design the receiver, and we are going to find out the probability of error, and it is possible to recover the signal in presence of the noise. Okay, so this completes module 3. This completes module 3, the theory part. Some problems are there. I'll take the problems. So just I'm going to recall what are the things we have studied so far. Okay, so just for the recall, I'll take here. So this is the random process. So what we have seen in the module 1 we are taken here. So for the random process, which is nothing but it's the random signal. If you are going to have it, it's a time varying function in the that one you are going to call it as a random process. For that one you are going to assign some real numbers we are going to assign. So that is a random process. For the random process at some particular time interval T1, T1 for the different types of random signals you are going to take. And if you are going to collect the data, we are going to call that one. The collection of the data, it is called as the ensemble averages we are going to call here. Ensemble averages or ensemble we are going to call. Ensemble is it's a collection of the signals. Okay. So similarly, afterwards we have seen the the probability density function for the random process. It will be defined at time t as a fx of t of x you are going to define, and as per the property of the post-spectral density, always it will be greater than 0. Okay, so for the bivariate random process, so if you're going to consider two random processes at the two different time intervals, so this will be defined as fx of t1, fx of t2 at x1 and x2 we can define. Okay, similarly for the multivariate we can define like this, multivariate random process. So similarly for the joint random process we can define like this in terms of x and y. So this is the multivariate joint random process. And we know the statistical independent events, so which is nothing but, so if the occurrence of one event does not depend on the occurrence of the other event, we can call that one as a statistically independent, we can call here. Okay, so based on that one, so for the any joint random process is there or any multivariate is there, we can express as the product of the individual PDFs. So same thing applicable for the multivariate and as well as the joint random process. And afterwards we have seen the concept of the expectation, so of the random process. So it's nothing but the corresponding PDF, the integral with random variable we are going to take. So similarly, the mean will be taken accordingly, and also the bivariate expectation, which is called as the joint expectation, we are going to consider accordingly. Okay, and we have seen for the joint random process also we can express the expectation, that is the correlation we are seeing in the module 2. The same concept is expanded for the random process. So next we have defined the concept of the stationary random process, in which, okay, so the signal is said to be stationary if its statistical characteristics does not vary the smallest change in the time t here. So okay, for this one, statistical characteristics is nothing but the mean and variance will remain the same, or the PDF also remains same for the small variation of the time, which is called as the tau here. Okay, so that one you are going to call it as that one it is called as the stationary random process. And for the stationary random process of order 1, order 2 we have seen, for first order and second order we have seen, and the variance will remain the same constant here, and second also we have seen. Afterwards we have introduced the concept of the Whiteson stationary random process. Whiteson stationary random process, in which, so for the two different time intervals, if its statistical characteristics remain same, you are going to call it as a Whiteson stationary random process. Okay, so this is the we have seen, and we have noted that if the stationary random process of order 1 and 2 are considered as a Whiteson stationary random process because its statistical characteristics remain same. Afterwards, we introduce the concept of the autocorrelation function. Okay, so which is the correlation of the signal with its delayed version, and we have seen the properties of that one. So many properties we have seen. At tau is equal to 0, that is called as the centered sequence. All these properties we have seen, and also autocovariance we have seen. It's the difference between the autocorrelation and its mean square value. Then we have seen the concept of the cross correlation. For the two random processes we are going to consider, it is a cross correlation, and Rxy of tau is not equal to Ryx of tau. It will be defined in the different manner like this. Okay. Similarly, we have seen the properties of the cross correlation and cross covariance we have seen. Afterwards, we have seen the addition of the random process. We added the random process, and we find the corresponding mean, and the multiplication of the random process we are done, and we find out the corresponding mean, variance, and as well as the autocorrelation function. We have seen this one. Okay, so right. Afterwards, you have seen some problems on the autocorrelation function and its product property. Okay, so afterwards we have seen the ergodic random process. So if the random process is taken for the time average, we are going to call it as the ergodic random process. So for that one, the autocorrelation function and for the autocorrelation function of the ergodic random process will remain same. So we can say it as the ergodic here. We have seen the example we have taken, and we have proved that the autocorrelation of both the functions are same, so it is ergodic here. Afterwards, you have seen the post-spectral density, which is the Fourier transform of the autocorrelation function, and we have seen some properties of that one. Okay, some properties of that post-spectral density we have seen, and we have seen one problem on this one. So one more problem is I'll take that one, and afterwards we have seen the concept of the linear systems. Okay, and the different kinds of noise, white noise and the thermal noise. So right, so this is about the module 3. So any doubts in any of the topics? Any doubts in any of the topics what you have seen so far? Any doubts so far? What are the topics we have seen? Any doubts? No doubts? No doubts in the topics?
No, sir.
Okay, so all the topics are understood, right?
Yes, sir.
Okay. So I think there will be no problem for attending the internals, I guess. Okay, so the topics are less, and also it's a repetition of what we have seen in the previous two modules, so that you can feel it's a bit easy when compared to the module 2, right? Okay, so let us take some, I have some two problems are there. Let me take the problems here. So we have taken the linear systems you have taken here. So just you can, I'll recall the formulas here. So formulas for the linear system. Formulas for the linear system. So we have the formula, that is the Laplace transform will be defined as h of s into x of s, and the corresponding in the frequency domain. So s is equal to j omega means it's in the frequency domain. It's a Fourier transform. In the Fourier transform, we can define like this: h of j omega into x of s. And similarly, the power spectral density, which will be given like this: h of j omega, the magnitude of the square into x of xx of omega, sx of omega. Done. So these are the formulas. And also for the noise, we have the power spectral density of the white noise will be equal to the some k constant here. Okay. Suppose if I'm going to give for the linear system, if I'm going to give the white noise as an input here, white noise as input, if you are going to give, so then the corresponding power spectral density for this one, if I'm going to give white noise as an input here, so that sx of omega is equal to the white noise will be there. So at that time, so then the power spectral density of the system will be given like this. Power PSD of the system can be given like this. So it is nothing but sy of omega is the power spectral density. H of j omega magnitude of the square will remain same here. And I'm going to give this one as a white noise I'm going to give, so it will become k here. For the system, I'm going to give this as an input here. Then the corresponding power spectral density of the system can be taken as k into h of j omega magnitude of the square. And also we have seen the variance of the system. So that is sigma n square. So it will be equal to the 2 kb for the white noise, variance of the white noise. Okay. Variance of the white noise will be equal to sigma n square is equal to 2 kb. Suppose if you are going to substitute k here, if you are going to substitute for k here, okay, k is nothing but Sn of omega. If you substitute here, so it will become equal to, so what we'll get is k is equal to Sn of omega. So this is also will become equal to, okay, you can substitute here sigma variance, no problem. So fine. So these are formulas we are seeing here. Like k can be substituted as Sn of omega, so that it will become 2b into Sn of omega. We'll get 2b into Sn of omega. So let us see one problem on this one. Okay, so take a network has a voltage transfer function. A network has a voltage transfer function. Voltage transfer function. Voltage transfer function. H of s is equal to 1 divided by s plus 3 into e to the power of minus 0.2s, e to the power of minus 0.2s. Okay, the input to the system, the input to this network, input to this network is a zero mean white noise, zero mean white noise with a bandwidth B is equal to 5 megahertz, and variance of 3.7 volt square. 3.7 volt square. Find the network's networks, output PSD, output power spectral density, Sy of omega, Sy of omega, Sy of omega. Okay, so taken, right? So here they given the transfer function of the linear system. They given h of s is equal to 1 divided by s plus 3 into e to the power of minus 0.2s. Okay, so this is the transfer function they are given here. The input to this one is it's a white noise. So white noise is the thing, so it's a that is we are seeing the white noise Sn of W. Okay, that is the power spectral density of the white noise. Okay, and it is having a bandwidth of 5 megahertz and variance of 3.7 volt square is there. We need to find out the output network power spectral density. We need to find out here. We need to find out the power spectral density of the output night. We need to find out. Okay, so we need to find the network of the power spectral, that is the output of the output signal power spectral density. We need to find out here. Okay, so done, right? Let us model the system. I'm going to take this one. So I can take. So it has been given the system. It has been given the linear system. So x of t. So this x of t is nothing but it's a white noise. The input to the system, it's nothing but the white noise. Okay, so h of t is it's a transfer function of the system. The output is nothing but y of t. Okay, so take this system. Take this system. Okay, so then this system Sx of omega. So since white noise is having so already we have seen that. So this white noise will be having the power spectral density of k. So since this is equal to the input signal, we can say that this power spectral density of input signal can be equal to the Sx of omega. We can take here. Okay, so since okay, we can take since we can take okay. Let us consider the parameter input to the linear system. Input to the linear system. You can take this one so that you'll be having better clarity. Will be there. Input to the linear system is the white noise. Is the white noise. Is the white noise with a zero mean. With a zero mean. Okay. Therefore, Sn of omega. So this is the power spectral density of the noise. So since it is equal to the x of t, I can take it as a Sx of omega we can take, and this will be equal to the k, because we know that Sn of omega, that is the power spectral density of the noise, will be equal to the power spectral density of the input signal. So this will be equal to k. So why I am taking the power spectral density? Because in the problem they asked you to find out the power spectral density of the output of the signal they asked here. That's why you are considering this one. Sx of omega is equal to Sx of k. And some of the data it has been given here. The data it has been given is nothing but they're given the variance, they're given the bandwidth, they are given, and they're given the transfer function. So let us take that one. So it is given. So variance sigma n square is equal to 3.7, and the bandwidth B is equal to, it is a 5 megahertz. So 5 into 10 to the power of 6 hertz. Mega is nothing but 6 hertz here. Okay. And we know that so sigma n square is nothing but we know it is equal to the 2k into b. 2k into b we know already, we have defined the formula. So from this one we can obtain the k. So k will be equal to the sigma n square divided by 2b. Sigma n square divided by 2b. So sigma n square is nothing but it's a 3.7. Okay. So it is equal to 3.7 divided by. So it is 2, the bandwidth is nothing but 5 into 10 to the power of 6. 5 into 10 to the power of 6. So what will become is 2 5s are 10. So it will become 10 to the power of 7 you will get here. 10 to the power of 7. So if it go to the numerator, it has become 3.7 into 10 to the power of minus 7 you will get here. 10 to the power of minus 7. Because 2 5s are 10 is there. So 10 into 10 to the power of 6 will become 10 to the power of 7. So it will become like this. So right. And also we have seen the, so any doubts in this one? And also we have seen the formula for the power spectral density of the output here. So this is the formula for the power spectral density. Sy of omega is equal to the h of j omega, the magnitude of the whole square, into sx of omega. Let us use this formula to find out the power spectral density. So you can take the power spectral density. We know that the power spectral density, the spectral density or power spectral, we can take power spectral density of output y of t is given by, so it is sy of omega. So this will be equal to the h of j omega, the magnitude of the square, into sx of omega, okay. So this is the h of j omega. H of j omega is the thing, but it is given in the frequency domain, okay. But in the problem they given the transfer function, they given in terms of the s domain, they given here s domain. So the relationship between the s domain and the frequency domain is the thing, but Fourier transform is s is equal to j omega. If you go to substitute s is equal to j omega, then Fourier transform and Laplace transform will become same here. Okay, so this is a transfer function. If I substitute s is equal to j omega, we are going to get the frequency response of the system. You are going to get frequency response. Okay, so you can take given